3.6 centimeter from the center, 4 meter from the center of the ring. Well, we know the radius is given, which is 8.5 centimeter, 0.085 meter. The charge carried by the ring is 2.75 microcoulomb. And in A, x equal to 0.012 meter. Well, we will use the exact formula for that. E equal to kqx over a squared plus x squared to the power of 3 over 2. Alright? Just replace all the values. Kq in coulombs times x, a squared plus x squared to the power of 3 over 2, and use this on your calculator and see whether you get that value. 4.7 times 10 to the 5 Newton per coulomb. Alright, and for B part, the only difference is x will now become 3.6 centimeter or 0.036 meter. That's the only difference there for B part. For B part, x equal to 0.036 meter. So everything else remains the same. We simply replace our x by 0.036, and that gives you the electric field 1.13 times 10 to the 5 Newton per coulomb. How about C? The radius of the ring is 8.5 centimeter. We want to find the electric field at a distance 4 meter. That 4 meter is fairly far compared with the radius of the ring. We can use the approximate formula there. Since x equal to 4 meter is very large compared to a equal to 0.085 meter, we can use the approximation. What is the approximation? The approximation is the point charge formula, E equal to kq over x squared. Well, you know the value of q, you know the value of x, we know k, so using that we get the equation, the value of electric field, 1.55 times 10 to the 3 Newton per coulomb. Okay, let's look at another situation. Field on the axis of a uniformly charged disk. There is the disk. You need to find the field on the axis. This is the axis of the disk. You need to find the electric field at a point on the axis of a uniformly charged disk. And you know what we're going to do? We're going to divide this disk into rings, because we know the electric field on the axis of a ring charge we just derived. So we're going to divide this disk into hundreds of thousands of rings. Find the electric field at the point due to each ring and add them all together. In other words, we use calculus, integration. Okay, let's do that. I'm going to run down on it a little too fast, and try if you can follow these steps. Consider a disk of radius r and charge per unit area sigma. Here is the disk. The radius of that disk is r, and the charge per unit area is sigma. Consider a ring of radius r. Look at this ring here. The radius of this ring is small r, and its width is dr. This width is dr. Alright, P is a point distance x from the center. This is the distance x. We need to find the electric field at P due to this entire disk. You can see in my diagram I have kept the disk flat like this, and the point P is on the axis here. And you can see I have cut one ring. The ring has a radius r and the width of the ring is dr. Can you tell me what the electric charge on that ring is? To do that, you need to find the area of the ring. Can you tell me what the area of this ring is? If you take the circle, the inner circle of the radius r, the circumference is 2 pi r, and if you multiply that circumference by dr, it will give me that area of that ring. I hope you understand what that area I'm talking about. I'm talking about this area. You see that? That area I'm shading in red. That's the area I want. Now, what is that area equal to? That area equal to this circumference, this length, the 2 pi r multiplied by dr. So the area of the ring is 2 pi r dr. And if you multiply this area with sigma, sigma is the charge per unit area, that will give me the amount of charge on that ring. The charge on the ring is this area multiplied by sigma, the charge per unit area. And now, the field at P due to this charge, we're going to import the formula we derived in the previous case, is dE equal to kqx over r squared plus x squared to the power of 3 over 2. This is the formula for the field at P due to a ring charge. And this q we are going to replace by 2 pi r dr sigma, or I will bring this sigma over to here. I will call it 2 pi r sigma dr. So I'm going to replace that q by 2 pi r dr sigma. Alright, let's do that in the next slide. This q will be now replaced by this quantity. So dE, the electric field at P due to this ring charge, is k times 2 pi r sigma drx over r squared plus x squared to the power of 3 over 2. And you can see x is a constant. But what will change is now this r, because the ring can be anywhere on the disk. This r can change from 0 to big R. Big R is the radius of the disk. Alright, you can now see I have taken out all the constant factors. 2 pi k sigma x are all constants. X is not a variable here. X is a constant. It's the distance of the point P from the center, times r over r squared plus x squared to the power of 3 over 2 dr. This is the variable term. Now for the total field at P, we integrate this quantity from, you see, this ring that we taken can be taken anywhere on the disk. From this r equal to 0 to this r equal to big R. So you integrate this quantity for r equal to 0 to r equal to big R, and it becomes the electric field at P is 2 pi k sigma x integral 0 to r over r squared plus x squared to the power 3 over 2 dr. And that is, I brought this 2 inside for convenience because I'm going to use a substitution to do that integration. Look at the substitution. Substitute r squared plus x squared equal to u. And if you take the differential now, remember x is a constant. 2r dr equal to du. So when the denominator r squared plus x squared is u, the numerator 2r dr will be du. So this, now use this to change the limits. We have r squared plus x squared equal to u. When this r equal to 0, then u equal to x squared. And when r equal to big R, then u will be x squared plus r squared. So when you make a substitution, you also need to take care of the limits. What does the integral now become? It will be pi k sigma x, integral 0 becomes x squared, and r becomes x squared plus r squared. Integral x squared to x squared plus r squared 1 over u to the power of 3 over 2 du. See, this is our u, and 2r dr is the du. And you know how to integrate this. That will be pi k sigma x, integral x squared to x squared plus r squared, u to the power of negative 3 over 2 du. And the integral of that will be u to the power of negative 1/2 over negative 1/2, using the power rule for integration. And the lower limit and the upper limits for u. And simplify this. You understand this, don't you? This negative, I brought it up here, and divided by 1/2 became multiplied by 2. That's how this became negative 2 here. And u to the negative 1/2 is 1 over square root u. And now use the upper limit, square root of, using the upper limit, replace u by x squared plus r squared, minus replace u by x squared, and you have this. Okay, now I can make this negative positive by simply exchanging these terms inside. Is that right? You know a minus b is negative of b minus a. And look at the equation we produced. The electric field is given by 2 pi k sigma x, 1 over x minus 1 over r squared plus x squared. Now that is a beautiful equation. But you know, most of you I know did not follow what I did. But if you did your calculus 2 well, then you will understand all what I'm doing here. Because the integration by substitution is an interesting part in there. But if you don't understand the integration, don't worry about it. But this is important, the equation. The electric field at a point on the axis of a charged disk is 2 pi k sigma 1 minus x over square root of r squared plus x squared. But all I did is I took this x inside the square, inside the bracket. When the x is taken in, x divided by x is 1, and that x stays on the numerator. Where sigma is the surface charge density, r is the radius of the disk, and x is the distance of the point from the center of the disk. Field at a point on the axis of a uniformly charged disk is given by this formula. For very large x, it will reduce to the usual point charge form kq over x squared. And when the point is very close to the disk, that means x is very small compared to r, then you can neglect x, or this x will be 0. When x is 0, this term will go away. So when x is very small, that expression will reduce to 2 pi k sigma. I want you to remember that. The electric field very close to a charged disk is 2 pi k sigma. When x is very small compared to the radius of the ring, this becomes, you see, that part will become 0, and the electric field will be given by 2 pi k sigma.